Welcome to a new video about embedded DSP design on FPGA. Today's topic is going to be about bandpass sampling. This is a really important topic in DSP design, and the reason why I want to mention this topic or talk about this topic is that my intention is to implement an FM radio on the FPGA at the end of this DSP design series. And for an IF of 10.7 megahertz, we need to digitize it by an ADC before the FPGA can demodulate it and recover the audio. So the question I have now for you guys, can we digitize this 10.7 megahertz with a 10 megahertz ADC sampling frequency? Or can we even sample it with 1 megahertz? In between, this is an FM IF frequency of 10.7 megahertz. It was captured on my essay before the LNA. And as you can see, the power is very weak, minus 44 dBm. So this is just on the side. This is so it occupies a bandwidth of 200 kilohertz, and it's exactly at 10.7 megahertz. Okay, back to our topic. So we learned that the Nyquist theorem states that in order for us to recover successfully the original frequency, we need to sample it by at least its frequency. So if you have 1 kilohertz, you need to sample it with 2 kilohertz at least. So like in the case for 10.7 megahertz, we need to sample it with 21.4 megahertz. That's true only for baseband signals. If you are interested in the spectrum from the DC all the way to the center frequency, yes, you need to use a higher frequency. Like in this case, you need to use 21.4 megahertz. But for my FM radio signal, it is bandwidth limited. It's only 200 kilohertz. So we are not interested in any spectrum between the DC and 10.6 megahertz. So therefore, we can use a lower frequency, a frequency that is at least twice the bandwidth of the FM, which is a frequency that is at least 400 kilohertz. So if the bandwidth is 200 kilohertz, so probably, I'm not going to confirm that, you can sample it with 400 or not, 400 kilohertz or not. But you don't need to use a higher frequency. You don't need to use 21.4 megahertz. I'm saying this because there are conditions for this bandpass sampling theorem also. Otherwise, if you don't respect these certain conditions, then your spectrum will be overlapped and with different Nyquist zones spectrum, and you will not be able to recover the signal you are targeting. Okay, so short answer, yes, for a bandwidth limited signal we can sample it with a frequency that is less than the center frequency. We can sample it with a frequency that is more or equal twice the bandwidth, not twice the FC, the center frequency. Okay, so this is a bandwidth limited signal. It has a center frequency, has an FL on the lower side, lower frequency, and has a higher frequency. The case of the FM, FL is 10.6 and FH is 10.8. Nyquist zones. When you sample a certain signal, you have Nyquist zone, and these Nyquist zones has to do with the sampling frequency. So the first Nyquist zone is between 0 and fs over 2. Second zone is fs over 2 to fs, and third zone between fs and 3fs over 2, and so on. So the equations in the top, k minus 1 times fs over 2, and the upper limit is k times fs over 2, and k is 1, 2 is an integer basically. So now, for our case, the first of all, before we look at the diagram at the top, look at the equation. When we sample a certain bandwidth limited frequency, it creates images, and these images falls at fs plus n times fs, and n can be plus or minus an integer, plus or minus 1, plus or minus 2, plus or minus 3. So for the case of 10.7, if we need to move it to the baseband, we can sample it with 10 megahertz, and in this case n going to be -1, and as you can see, so 10.7 falls at the third zone, zone number 3, which is fs to 3fs/2, and when we sample it with 10 megahertz, it's going to alias to an fs equal 0.7 megahertz as per the equation below. This is the theorem, and just take it as it is. Okay. The good news about this selection of the fs, there is condition also. You cannot select any fs you like, so the fs has to meet certain conditions, and these conditions are these. Your fs needs to be between 2fh/k and 2 times fh minus bandwidth over k minus 1, and k is an integer, and that k, it needs to be less or equal than fh/b, which is the bandwidth. Later we're gonna go and look at an example, a works out example, and we verify if our sampling frequency meet these conditions. So because this sampling frequency needs to meet this condition, if it doesn't meet these two conditions, our spectrum will overlap and we won't succeed recovering the spectrum we're interested in. So that's what happens. So we are in third zone, and we will manage to shift. That's called down converting, by the way. We will shift the spectrum of 10, sorry, the center frequency of 10.7. We will move it to an FC, will alias to an FC equal 0.7, and this way we can sample it. We can filter it using a low pass filter, and then have the FPGA process the bandwidth of the FM we're interested in. Is it even possible to sample this IF frequency with 1 megahertz? The answer is yes, it is possible, and I can walk you through how it looks like when you sample with an FS equal 1 megahertz. So, but first I think we need to go and look at the example, make sure our sampling frequency meet the conditions we just talked about, and therefore will be no overlap no overlap of the spectrum between different zones once we sample with 10 megahertz. So these slides were prepared, were taken from based on the information I gave on a post I did on my website, embeddeddesign.org, and I urge everyone who's watching this video to take a look at this post and read through it. It has a lot of information. Unfortunately, I would not be able to cover all the information on these slides, and I urge everyone to take a look at the website and read through the post to understand all these concepts I discussed over here. So let's go and take a look at the website and the worked example. So this is the website where we're going to look at the worked out example. So if you want to access this web page, it's on embeddeddesign.org, and once you are on the website, you go to project FPGA projects, and from there you select bandpass sampling. So there's a lot of information here, as I said before, that I can't cover in these slides. You are encouraged to take a look at this posting and read as much as you could. There's a lot of useful information over here. So this is the workout example. So we have a lower frequency of 10.6, so the bandwidth is 200 kilohertz. So the highest the upper hand, or the highest frequency is 10.8 megahertz. So FH minus FL is 200 kilohertz, and the center frequency is 10.7 megahertz. So if you want to find a valid range of k for the values of k, then k must be less or equal than fh divided by the bandwidth. So fh, we found out that it is equal to 10.8 megahertz, and our bandwidth is 200 kilohertz, so that gives us 54. So we can choose a k that is less or equal to 54, a value of 54. So for the selection of the FS, the sampling frequency, so we want to have a sampling frequency that is between 2 times FH over K and 2 times FL over K minus 1. So if we plug in the numbers, that gives us a K that's more or equal to 3. So if you want to select a value that's going to work for our sampling frequency of 10, we need to have a K of 3 or more. So in this case, we found out that for the case of k equal 3, we found that our frequency lies really well within the range. So for a k equal 3, we found that the upper band is 10.6, and we found that the lower bound is 7.2 megahertz, and 10 just fits in nicely in between this range without any chance of having an overlap with other adjacent Nyquist zones. So that works out pretty well. So again, we cannot just select any IFS, any sampling frequency, to perform some type of undersampling. So the center frequency has to match the conditions I mentioned above. K, it needs to be less or equal than the highest frequency in the bandwidth divided by the bandwidth itself. Like in this case, K needs to be less or equal to 54, and not only that, Fs also needs to be between a certain range, as you can see in the equations in the second equation. So as I said again, so 10 megahertz turned out to be a good choice, and it would not cause any overlap, and it would allow us to successfully recover the audio from the modulated signal. Another selection we could do, we could also select Fs equal 1 megahertz. So I did my math over this, and I found yes, Fs equal 1 megahertz is a good choice, and I did my simulation for that, and it works out pretty well. So it is probable that if I implement, or when I implement the FM radio on the FPGA, I will go for an Fs equal 1 megahertz. It's a lower frequency, so let's say if you have a limitation on the bandwidth of the filter, of the ADC, then a choice of 1 megahertz is a lot better than 10 megahertz. And just a reminder here, if someone gets interested, like if you hear like 1 megahertz and be like, okay, I can use the XADC on the FPGA, you cannot do that. So the XADC on the 7 series of the FPGAs is not going to work. You can sample up to 1 megahertz, but the ADC itself has a limitation on its bandwidth, so you have to have enough bandwidth that's going to accommodate the 10.7 megahertz, and the maximum bandwidth of that XADC on the FPGA is 1 megahertz, so it's not going to work. And you can try, but it's not going to work. Okay, so this was just a quick example to validate that our sampling frequency is correct, is not going to cause any overlap with other adjacent Nyquist zones, and I showed you how the math was done on that. So a few things here I want to mention about this undersampling theorem. You have to be careful when you do your undersampling. You need to worry about your anti-alias filter. So basically, if you sample, let's say in our case, with 10 megahertz, that means any frequencies below 5 megahertz, it's going to pass through and then can cause distortion of your signal of interest. So what you need to do before you do undersampling, or before you process your analog signal with an ADC, you need to have an anti-alias filter. So in my case, I have 10.7 megahertz is my center frequency, so I needed a bandpass filter with a lower frequency of 10.6 and an upper frequency of 10.8. So this way we are sure we are selecting the frequency of interest or the bandwidth of interest, and then we undersample it so that we can recover it later on after we downsample and after we demodulate. So the process is like this. So you have a bandpass filter, which is an anti-alias filter, and then you do undersampling, and then you mix the signal. Like in this case, we found that the sampling of 10.7 with a 10 megahertz will make the spectrum lands at 0.7 megahertz, so you need to move that 0.7 megahertz into the baseband, and the way you do that, you need to use a mixer. So you have to mix it so you can bring it to the baseband, and on top of that, you have to use a low pass filter to filter out the high frequencies, and after that point, you can start to use your FM demodulator to recover the audio. So anti-alias filter is important in this case, and we talked about the bandwidth. The bandwidth is very important of the ADC. And then the ADC aperture jitter. This is what we're talking here about the clock of the ADC. The clock of the ADC, if it has a jitter on it, it's going to affect the it's gonna affect the window of the like where the after you undersample where the spectrum will land. So it is very important. So you can read more about that in this posting, and I think this is pretty much it. So you can read more about all this stuff, a lot of information here. So I just want to make this this video very quick, so we can now we can move into the live demo on System Generator. So on the System Generator, I will validate or verify with you guys live how 10.7 how it's gonna get aliased with 10 megahertz sampling frequency, and how it's gonna get aliased when it is sampled with 1 megahertz. So I will do a single tone, and I will do also a simulated FM signal. Okay, we will move there. It's done. Okay, so now we go to our workspace, and we have 10 megahertz here. We'll run it and see what's gonna happen. Great. So we got we covered our FM signal. So let's change the scaling on the x-axis just to make it easy to see. So let's move this to 1 megahertz, and here you go. So we got our spectrum centered at 0.7 megahertz as we expected, and we have a bandwidth of 200 kilohertz with a lower frequency of 0.6 and an upper frequency of 0.8 megahertz. So now let's quickly go and change the sampling frequency to 1 megahertz. So let's do that quickly here. I don't want to take too much time of your time. So let's change this to 1 megahertz and quickly run it, and then we just save and run. There you go. It's running. And it is done. So now we can go to our workspace again, and then change the sampling frequency to 1 and save and run. There you go. So this is our spectrum. Now we have a center frequency of 0.3 megahertz as we expected, and we have a bandwidth of 200 kilohertz, and we have side bands spaced by 5 kilohertz, which is the message signal. So now probably, if you guys don't mind, I can do a single tone and see how it is. So let's get rid of this, we don't need, and we can just use a single tone over here and see what's gonna happen and how it's gonna alias. So let's move this here and then change this to, let's just make this 0. This is just sampling frequency, we don't care too much about it. And let's make this 10.7 megahertz, e to the 6, and apply. Okay, and then save, and then we run it and see. So it's done. Let me remember here what we did. So we did, I believe, 1 megahertz sampling frequency. So we go back to our code here, and we have 1 megahertz here already. So we just run it and see what we get. So exactly, we get 0.3 megahertz as we expected. So maybe now we go back and change that to a sampling frequency of 10 megahertz and see what's going to happen. Just quickly here we do that. Apply. Okay, save and run it. So it's done. So we go back to our workspace and we change this to 10 megahertz instead of 1 megahertz for the FS, and we run it. So let's see here, change the scaling over here on the x-axis, and we make this thought we can change it. Why it doesn't give us axis properties? Change this to 1. Hit enter. So exactly, so we got a frequency alias at 0.7 megahertz, and that's exactly what we expected. So I'm not sure if I mentioned how this data gets exported. So this data gets exported to workspace by using this block called to workspace, and I named it ADC out. So this is pretty much it in terms of this live demo. So I hope you guys learned something from it. So now I'm gonna go back to our PowerPoint slides and conclude this video. So I used the post I mentioned that I have on my embeddeddesign.org website. So please feel free to take a look at it and read through it in details for more useful information. And if you guys enjoyed this video, please hit like, give us your comment, tell us your feedback, and subscribe and share the channel with your friends and your colleagues, and support the channels. So next video is going to be second part of this Bandpass theorem. So I would like to do a live demo on the FPGA itself, not just system generator. I will take a couple tones or whatever, maybe even an FM signal, and then undersample it, and we can look on the ILA how the signal gets aliased. And if I take a single tone, let's say 10.7 megahertz, and I sample it then with an ADC at 10 megahertz, then I would expect to see at the ILA a 0.7 megahertz single tone frequency. So we will demo that on the hardware and learn something together. Until then, I wish you all the best, and good night and good luck.